back to problems from chapter 13. We're in dynamics. As promised, I'm going to be doing some problems from the actual problem sets. In this chapter, I feel like a lot of people kind of drop off. This is where things kind of get a little complicated. So I just wanted to do a few more problems from the actual problem set to just give you even more practice. And the problem I picked sort of involves finding that angle psi, which is we look at in the book. They kind of explain how we get the angle psi, which is what the angle that the tangent line makes with either the radial line or the axis theta, depending on how you look at it. So yeah, I wanted to give a few problems where we practice that, because the fundamental problems in this one didn't really cover that. So yeah, let's dive into this. So here we have rod OA rotating counterclockwise with a constant angular velocity theta dot. So what I like to do is just extract all that information that they give us. The double collar B is pin connected together such that one collar slides over the rotating rod and the other slides over the horizontal curved rod, of which the shape is described by the equation R equals, so we have our R equation, or our precision equation. And it's a bit loud is because I have the AC on right behind me, and it's one of those crappy ones that apartments have in LA. So yeah, so bear with me. So we have the position one. If both collars weigh 0.75 pounds, determine the normal force which the curved rod exerts on one collar at the instant theta equals 120. So at the instant theta equals 120 degrees. Notice how they're giving us degrees and radians here. So just be careful when when you're punching these numbers into the cosines and sines into your calculator. Make sure you're using the correct unit. So either convert 120 to radians right away, or just go back and forth in your calculator. But just be aware that you have radians and you have degrees. You have to switch your calculator to mode rad or mode deg. The degrees and radians. Okay. So yeah, let's just start with the derivations first. Let's do r dot. All right, take the one time derivative first. You should get 1.5 sine theta dot, and then you do the second time derivative, and let's see, you should get 1.5. Remember what I've done before. We look at the first one, we get cosine derivative of sine theta, time derivative was cos theta, theta dot times theta dot. So you have that plus sine theta derivative of the second term, which is this one right here, theta double dot. Okay, and this is our r dot, r double dot. Let's evaluate those at the instant that they're telling us. So let's evaluate. All right, I haven't even started drawing forces or anything. I just want to first, let's just get the fundamental parts down. So when I evaluate this at theta equals 120, you should get 3.75 feet. Okay. This should end up giving you 6.495 feet per second. And then this one, our double dot, it should, I got minus 18.75 feet per second squared. Okay. So I have that. Also, one more thing that we gotta add is we have a constant angular velocity theta dot, which means our theta double dot is going to be 0. Okay. Let's put this in. If we want to convert it to radians, we're just gonna do pi times 180, right? And then that's I don't know. 6 goes into the. Let's see. That's 2 pi over 3. All right. So that's in radians now. And again, go back and forth however you see fit, right? Now, the next thing is, let's just get the accelerations out of the way. We know we're going to need them because we're going to be doing the equations of motion, right? We're going to do forces in the r direction, forces in the theta direction. When we do this, we're going to have, let's write down the equation first for the radial acceleration, and then theta dot squared, and then for the angular acceleration, or the angular component of the tangential acceleration, r theta double dot plus 2 r dot theta dot. This is one of those things that your professor gives you a cheat sheet, just write them down, or just I hate saying memorize them, but yeah, I guess you can memorize them, but it's kind of useless. You can always go back. You should always be able to go back and just look at what the equation is. You just gotta know how to apply it, right? So when we plug in all the numbers that we have r dot, r double dot, theta dot, theta double dot. So we have everything needed to calculate accelerations, and we end up getting minus 112.5 feet per second squared. Ugh. And then we get 65 feet per second squared. Okay, so now the a theta, I ended up getting 64.95. I just rounded it up, so roughly 65 feet per second squared. Okay, now we're here. Now let's begin looking at the forces. Okay, so let's see, what color shall we use? Green, maybe. Okay, so I'm gonna try to draw large. Well, yeah, it's kind of hard. All right, so this is the part. This is the pin. Okay, over here. Then we have the tangent to this the circular path. It's going to be a line that hits the circular path at one point only. Okay, so we can kind of so it's going to be something like this. Okay, so let's translate that over. So let's just draw it out. Okay, let's just say this is the tangent. Okay, now let's say the theta axis is going to be it has, well, let's try the radial axis first. Right, so this is a radial. So here it kind of looks like the tangent and the theta axis line up, but that's just because my drawing sucks here. This is theta, right? Let me for visual purposes, let's draw the tangent a little more. I don't know, exaggerated. So let's say the tangent is like this. That way, theta and r don't line up. So, right, because we don't have the path defined, right? The forces acting on this on pin B, on collar B, aren't just directed along the r-axis or the theta axis. So this requires us to find the psi angle, right? So we have to, if you look back at the previous section, the book tells you if the path is undefined, right? If you don't really know it, you have to follow this formula here. Okay. So what does that mean? We have r, and then we just take a derivative of r with respect to theta. Remember, there's not a time derivative. We're doing just a derivative with respect to theta. So here we, just what's r? It's 1.5 times 2 minus cosine theta divided by the derivative of r, which is 1.5, and then the derivative, what's inside the parentheses, we end up getting minus sine theta, so we just get sine theta, right? This goes away, right? Let's evaluate this at theta equals 120, okay? And then you should get 2.88, okay? From here, let's take the inverse tangent, and then, so next step is take the inverse tan, and you get the angle of psi is 70.89. Right, so far it's pretty straightforward, right? We did this basic stuff, the r dot, r double dot, theta dot, theta double dot, right? And this is pretty simple, right? You just have to identify, okay, my path is undefined, right? That circular path is undefined, so let's find psi first, right? And this is going to be measured from the tangent to the radial axis. So this angle here is psi, okay? I usually don't use psi for everything. I end up always using I don't think it's the complementary angle, but let's just call it complementary angle of psi, or sorry, phi. Okay, which is, this whole thing is 90 degrees, right? The angle between r and theta, because it's a perpendicular coordinate system, right? So it's 90 minus psi, and then you end up getting phi is 19.1 degrees. Okay. So far we haven't really touched the forces. We just kind of split our. We just found the angles between the tangent and the radial axis. Okay. Now is where this is where you have to have a lot of confidence. It's okay, I know where my forces are acting. One thing to note, these problems always will tell you that it's over the horizontal, right? So over the horizontal, that means think about this thing moving on a table, like on a flat surface, right? So we're not looking at the weight, so we don't have to take into account the weight, okay? So what you have to take into account, though, is the normal forces that are acting on collar B. So we have the normal on collar B, okay, exerted by, just the, what's it called? What's the other collar? Well, between the two collars, there's going to be a force that's normal, and it's going to be acting along the theta axis, okay? This one's kind of given, okay? And then there's going to be another normal that is the normal from the collar on the pin, I guess, or the double collar B is pin connected, right? So one of the pins is experiencing a normal by the pin that's underneath, and then a normal force on pin B by the collar that it sits on. Okay, and this is the normal force that it's going to get a little tricky. So we look here, right? It's going to be normal to the one back here. Okay, the one that's like I guess like the one that I highlighted, the one that's like behind the front collar, okay? That one's the one that's causing a normal force downward on the collar B. And that's, it's going to be at an angle. Right, so it's going to be sort of going down. This is how I drew it going. This is the other normal. Okay, so the normal done by the front collar, which is just going to be pushing it on the theta direction, and then the normal done by the collar in the back, okay, which is going to be perpendicular to the tangent, okay. And then from here, so remember this N will be perpendicular to the tangent, okay. So that's all we need, that phi. Okay, so hopefully everyone's with me here. Okay, so what's next? Well, now let's just solve for. We're solving for the determine the normal force which the curved rod, okay, exerts on one collar. So we're looking for N. Okay. So let's see, which equation can we, if we do N theta, I mean we can do N theta, but then we'll have two unknowns. If we do forces along the radial direction, okay, so let's write down what the forces are in the radial direction. We have and remember that this angle over here is phi. Okay, so we're going to have minus N because it's pointing in the negative R direction. Cosine 19.1, okay, and that's the only force that's acting on collar B, right, or the collar that's closest to us, right. That's the only force that's acting on it, right? So that's the only force. That's the only force in the R direction that's acting on the front collar. So that's all, right? Equals mass times acceleration, right? So the mass is 0.75 divided by 32.2. Remember that. Remember that they always, when you're given pounds, you're always given the force and not the mass. And then times, where's AR? AR, where are you? There you are. Minus 112.5. Okay. Crunch the numbers, like Michael Scott likes to say. Crunch the numbers, and this is positive. And then you end up with 2.77. Oh, I was going to say, not newtons, pounds. I almost switched the whole units across the Atlantic. And that's it. So this is the normal that the curved collar, so the one behind the front collar, is exerting on the front collar. Okay, and that's it. That's how we do these problems. A challenge for you guys: try to pick one of those fundamental problems that we've done in the past, so like the previous problems that I did, and the path there are kind of defined, like, so it's not necessary to do psi, but try to do the psi anyways, and you might get that psi is going to be like, I don't know, 90 degrees or 45 degrees, or some angle that makes the math a lot easier than when you get a psi of 70.89. Okay, so try that. If you guys have other comments, questions, concerns, please comment down below. Don't forget to like the video and subscribe if you need to. There's one problem that I was trying to do, 1391, and I finished it, but what I want you guys to do, if possible, is like, if you're in class, ask your professor to do problem 1391 from this book, and see how he comes up with the position equation, because I just don't agree with how the book does it some other crazy way. And yeah, I have my opinions on it, so I won't be publishing that one just because I don't agree with what the book says, and I don't want to confuse you guys. But I'll be doing some other ones shortly. I think I'm doing the next few will be 1392 and 1305 through 07. Alright guys, thanks so much for your time and attention. Go get them.